Good morning. I'm Joe DeRose. I'm a Brookhaven staff scientist at Brookhaven National Lab, and today I'm going to be telling you about combined clustering and weak lensing using the DESI Y1 dataset and stage 3 weak lensing surveys. This is work that was done in the DESI collaboration and in particular in the clusters, clustering, and cross-correlations working group, aka C3. Before I get started, I just want to say thanks to our sponsors and participating institutions. Without them, this science would not have been possible. And okay, let's jump in. I'm going to start with a bit of an overview of how we do cosmological inference. So we believe that all of the large-scale structure in the universe is sourced by a stochastic process, namely quantum fluctuations plus inflation. And that means that all the inference that we do in cosmology is statistical in nature. So we can't predict the individual positions and velocities of galaxies. Instead, a large part of what we do is make maps of things. In this case, I'm showing you a map of dark matter that I took from a simulation that I ran. So I'm going to show a few maps like this today. In the polar direction here, you're seeing the map in the plane of the sky, and then along the radial direction here, you're seeing the map along the line of sight, or further and further away from us back in time, or higher redshift. And so what we do is we take summary statistics of these maps and we compare them to our models and use that to learn about the universe. And one of our favorite summary statistics is something called the power spectrum. And this is just the Fourier transform of a map like this. So we get a Fourier transform of a density map delta at some wave vector k1, multiply it by delta at some other wave vector k2, and then take the ensemble average of this product over different areas of the sky. And that gives us something that we call the power spectrum, P of k. And the matter power spectrum is what I'm plotting in this figure here. So on the y-axis is the matter power spectrum, and this tells us about how much variance there is in the matter field at a given scale given by the wave number k. So k you can think of as an inverse distance. So on the left you see larger scales, and on the right you see smaller scales. On the points that you see here are measurements that we've made of the matter power spectrum from a number of different surveys. So in blue, orange, and green, you're seeing measurements that we've made from the cosmic microwave background from the Planck satellite. And then in yellow, red, and purple, you're seeing measurements from galaxy surveys over here. And this black line is a fit to the cosmic microwave background data using a lambda cold dark matter model. So this is our standard model of cosmology. And so this fit that is just under the CMB data also goes through a large number of the galaxy points. So on a log-log plot, all of this data that you see here agrees with lambda CDM. But if that were the end of the story, this talk wouldn't be so interesting, and cosmology in general wouldn't be so interesting. So there are a number of interesting deviations that we're observing from lambda CDM. And you should see the next talk for an in-depth discussion of H-naught neutrino and dark energy physics with the DESI data. In this talk, I'm going to focus on something that's called the growth of structure tension, and in particular, how we can measure the growth of structure from weak lensing and galaxy clustering. So what is the growth of structure tension? Well, it is just the tension between measurements that we make from the cosmic microwave background. So by measuring the CMB, we can measure the amplitude of structure at redshift 1100 and then extrapolate that to redshift 0 using lambda CDM. And that's what you see here. So this is essentially the amplitude of the matter power spectrum times the matter density at redshift 0 predicted by the CMB measurements. And what we have seen over the last number of years is that galaxy lensing measurements prefer a lower amplitude of structure at redshift 0 than these predictions that we can make for this amplitude from the CMB. And last year, a new interesting wrinkle was added to this picture, which is that galaxy clustering measurements from DESI prefer an amplitude of structure that is consistent with the CMB, although with significantly larger error bars. So the rest of this talk is going to be about how we can use the combination of weak lensing data and galaxy clustering data to both improve that error bar that I showed you that was relatively large on the DESI data, but also to tease apart systematics in the individual data sets I'm going to be talking about. So DESI is shown here in black, the DESI Y1 data. The Atacama Cosmology Telescope CMB data is shown in green. So this is a ground-based CMB telescope. And then there are 3 different galaxy lensing surveys I'm going to be talking about today. So the dark energy survey shown in purple, the kilodegree survey shown in black, and the hypersuprime cam year 3 dataset shown in blue. So the rest of the talk is going to be broken down into 3 parts. The first will be about, just general overview of weak lensing and how DESI can contribute to weak lensing. And then I'll tell you about how we can use those data sets to calibrate weak lensing systematics with DESI to try to understand if the differences I was showing you between the CMB measurements of the amplitude of the matter power spectrum and galaxy lensing are driven by systematics or by fundamental physics. And then at the very end, I'm going to tell you about how we can tighten up that DESI error bar using combined analyses of weak lensing and DESI clustering. So let's get into it. What is weak lensing and how can DESI contribute? I'm going to be talking about 2 different kinds of weak lensing today, the first of which is galaxy lensing, and then in a second I'll tell you about CMB lensing. I think this figure nicely illustrates the effect of galaxy lensing. In the background, you can see images of galaxies as we would observe them on the night sky, unlensed in their natural state. And so what happens is as photons propagate from these galaxies through the intervening matter distribution in the universe, they're deflected by potential wells. And that means that the images that we observe of these galaxies are distorted with respect to the unlensed images of these galaxies. And those distortions or shears are correlated with each other. So we can measure the correlation between the shapes of different galaxies. So we can measure shape correlations. And that tells us about how the amount of structure there is in between those galaxies and us and how that structure is growing over time. The other thing that we can do is cross-correlate the positions of galaxies that trace this structure in between this background source galaxies and us with the shapes of those background galaxies. So this is something called galaxy-galaxy lensing. And that correlation also tells us about the structure in the universe. So we can do shape, and position shape correlations. Both of these are weak lensing measurements using galaxy lensing that are powerful probes of the matter distribution in between us and those galaxies. An analogous effect called CMB lensing uses the cosmic microwave background photons as a source for lensing rather than galaxies. So the way this works is we understand what the statistical distribution of the cosmic microwave background temperature and polarization fluctuation should look like. And lensing imparts a particular distortion on those fluctuations that we can use to back out to reconstruct the matter distribution. So what I'm showing a very exaggerated version of that distortion over here on the right. So photons, as they propagate from the cosmic microwave background to us, are again deflected by the intervening matter structure in a way that imparts a particular correlation in these temperature and polarization maps that we can use. And the leading effect that this has is to correlate different modes, different scales in the cosmic microwave background maps in a way that otherwise would not be correlated. So we can use these correlations to reconstruct the matter distribution in between the CMB and us and learn about the projected matter distribution between the CMB and us. And finally, I would be remiss if I didn't tell you about how we can use galaxy clustering to extract cosmology from galaxy maps. After all, this is a DESI talk. So I'll tell you a bit about that right now. And again, we're going to make maps. In this case, we're making maps of galaxies. So I'm showing you one such map here. And what you'll notice is that if we take the power spectrum of this map and compare it to the matter power spectrum, you get quite a different answer. So this orange line here is the galaxy power spectrum. And this blue line here is the matter power spectrum. So it's really this matter power spectrum that we need measurements of in order to infer fundamental physics, or at least in order to infer things about the growth of structure. And so we get that kind of more directly through lensing, but through these galaxy clustering measurements, we get a biased answer when we just measure these galaxy power spectra. And that's because galaxies form in the most overdense regions of our universe. And that imparts this difference between the galaxy power spectrum and matter distribution. And this difference is something that we call galaxy bias. So this depends on galaxy formation physics that we don't understand ab initio. And so it's really hard to tease apart the difference between growth of structure in our universe by measuring these galaxy clustering statistics and just differences in galaxy formation physics. But luckily in spectroscopic surveys, we have a different sensitivity. We don't just measure the positions of galaxies, Along the site, we're also sensitive to the velocities of galaxies. So the difference between these two maps that I was just showing you is a smearing out along the line of sight that is due to an effect called redshift space distortions. And so this effect comes in because the redshifts that we measure of these galaxies have slight perturbations to them, depending on whether those galaxies are moving towards or away from us with respect to the bulk expansion of the universe. And so that those distortions break the isotropy of the galaxy distribution in a way that we can use to actually infer things about the growth of structure directly from these galaxy maps that is relatively independent of galaxy bias. And so the way that we do that is we measure power spectra in the plane of the sky, and then we measure them also in the line of sight, roughly. So you can see those different measurements. Plane of sky measurement is orange here, and the line of sight measurement is in green here. So the plane of the sky is sensitive to just the positions of galaxies, whereas the line of sight measurements are sensitive to the positions and velocities of galaxies. And so by jointly analyzing these two spectra, we can disentangle the impact of the velocities from just the positions, which have this galaxy biasing effect. And the velocities, it turns out, have to have the same distribution as dark matter on the largest scales. And so we can use those that inference of velocities to learn about how structure grows over time using just these spectroscopic galaxy survey maps. So that's also a very powerful probe, especially given that now we have the largest map of galaxies that we've ever made using the DESI using DESI DR1 and now DESI DR2. So you heard about DR1 in the last talk from John, and Enrique is going to tell us about really nice BAO result from DESI DR2 in the next talk. So you can see this beautiful map that we've made from the DR1 data set here. And really the main point of this talk is that we have each of these individual probes, but because they're all sensitive to the same underlying matter distribution, they're correlated. So we can use the cross correlations between these things to improve our constraints on cosmological physics. But we can also use them to tease apart the systematics that exist in these individual data sets, like intrinsic alignments, redshift calibration, the impact of foregrounds on the CMB maps. And so I'm going to be talking about the systematics first, and then I'll tell you a bit about cosmology. So let's jump into the systematics and how we can calibrate weak lensing systematics with DESI. The first thing I want to talk about is something called galaxy intrinsic alignments. So when we measure the ellipticities of galaxies, we're not just measuring the gravitational shear, and that's because galaxies are not spheres. They have some intrinsic ellipticity to them, and this intrinsic ellipticity is many times larger than the average gravitational shear that we're looking at in these weak lensing surveys. And so we have to average over many galaxies in order to get a statistical measurement of this gravitational shear. But it turns out that these intrinsic ellipticities are also they also can be aligned with them they also can be correlated. And those correlations, when you average over many galaxies, don't average down to zero. And so you get a contribution to our ellipticity correlation functions. So these these shape correlation functions or position shape correlation functions that I was telling you about, that comes from this intrinsic alignment effect. And it turns out that this is a very important effect for galaxy lensing and something that needs to be dealt with in order to obtain unbiased cosmological constraints. But very powerfully with DESI data and spectroscopic data in general, we can directly measure these intrinsic alignment signals for a subset of the galaxies that we use in these lensing studies. And the way that we do that is as follows. So in these spectroscopic surveys, we measured the distances to galaxies very precisely. And then for those galaxies that we have precise distances to, we can also get shapes from these weak galaxy lensing surveys. And then we can cross-correlate the shapes of those galaxies with the positions of those galaxies in very narrow redshift ranges. And the reason that we want to make those ranges very narrow is because that allows us to essentially remove the impact of lensing. So usually we want to measure lensing, but by making sure these redshift bins are very narrow and cross-correlating positions of galaxies with shapes of galaxies in those narrow redshift ranges, there's essentially no lensing impact. And so all we're measuring in these shape position correlation functions here is the impact of intrinsic alignments. So one such type of statistic that you can measure is this WG plus statistic. So that's a position shape correlation like I was just telling you about. And these are some preliminary measurements that we've made using DESI in a paper that is going to be released quite soon. And so the different points here are different different absolute magnitude cuts of the luminous red galaxy sample. So the black points here are the brightest, and the yellow points here are the faintest. And you can see there's a strong trend between the luminosity or magnitude of these galaxies and how strong their alignment signal is. And so by making measurements like this, we can inform the intrinsic alignment models that we apply to our cosmological constraints. And if we're able to measure these statistics over a wide enough range of galaxy types, then we can really convince ourselves that we understand this intrinsic alignment signal very well, and worry about it less when we do cosmological constraints, or at least know that we're treating it with the uncertainties that it deserves. And so one really powerful thing with the DESI data is that we're able to do this type of measurement over a much wider range in redshift and much wider range in galaxy type than has ever been done before. But we still have a ways to go before it's as powerful as we need it to be in order to make this a subdominant systematic. The next thing I want to tell you about is measuring photometric redshifts and calibrating those photometric redshifts with DESI data. So why do we need to know the redshifts of galaxies in order to do weak lensing science? That's because how much a galaxy is sheared depends not just on how much matter there is in between that galaxy and us. It also depends on the distance, the whole geometry of this lensing system. So the distance between the galaxy that's being sheared or lensed and us, the galaxy that's being lensed and the thing that's doing the lensing, and also the distance between the thing that's doing the lensing and us. So all of these distances matter. And the problem is that in these galaxy lensing surveys, because we need to measure many, many galaxies, we don't get precise redshifts to them. We just have the images of the galaxies. And these images and colors in those images really give us imprecise measurements of the distances to these galaxies. But luckily, DESI can help with this by statistically calibrating the distributions of distances as a function of color in these images. And we've been doing just that with DESI data. So we have a powerful new catalog of deep DESI spectroscopy in something called the Cosmos field. So this is a small field that has frequently been used to do this distance color or distance photometry relationship calibration in previous weak lensing studies. And so this figure here is showing the if you break this DESI catalog down into different color regions and compare how many redshifts we have in this catalog to the catalog that was used to do the kilodegree survey redshift calibration, we have about 1.6 times as many galaxies in each part of color space in the DESI catalog than was used in this KIDS data. So that's a significant improvement in the number of galaxies that we're using for this calibration. You can see, there are also regions of color space where we have many, many more galaxies. So that's really powerful. And we've gone ahead and used this new catalog, which we understand quite well, very well, because we've made consistent quality cuts on it because all of the data is observed with the same instrument, DESI. And so we're able to calibrate redshift distributions from these lensing surveys and see if we get the same answer as they do when it comes to cosmology. So the black lines here are the fiducial redshift distribution calibrations that these different surveys put out. So the dark energy survey here, hypersuprime cam survey here, kilodegree survey here, and the different rows here are just different redshift bins. And the purple histograms that you see here are the parts of these redshift distributions that we can calibrate using the DESI data. So for a lot of these bins, you can see we can calibrate a large portion of them with just DESI data, which is really, really powerful. But you see for things like HSC, it's a bit harder to use DESI data because these are very, very faint galaxies. But we do have programs in DESI that are going out and trying to get at these fainter galaxies and do a similar calibration. So that's something to look forward to in the more distant future. But the upshot is when we use these DESI calibrations of these redshift distributions to do cosmology with these surveys, we get a consistent answer to what these surveys put out. The last systematic I want to tell you about is measuring the distribution of baryons with the Sunyaev-Zeldovich effect. So what is the Sunyaev-Zeldovich effect? In particular, I want to tell you about the kinetic Sunyaev-Zeldovich effect. So this is an effect that comes in when a cosmic microwave background photon inverse Compton scatters off of a free electron that's moving in the intervening matter between the CMB and us. And when it scatters off, it receives a an apparent temperature increment or decrement. And so we observe correlations between temperature increments and decrements and the density and velocity distributions of free electrons in our universe. And the thing that's very powerful is with DESI, we can actually reconstruct the velocity distributions in our universe in the areas and volumes where we have DESI galaxies, using a similar technique to what we use to do baryon acoustic oscillation reconstruction, which is a very important thing for Enrique's talk, but also powerful for this because it allows us to get at the velocity distributions on large scales in our universe. And by doing that, we can disentangle the density contribution to these kinetic Sunyaev-Zeldovich effect, to this kinetic Sunyaev-Zeldovich effect from the velocity impact, and basically directly probe the density distribution around the baryon distribution, or the distribution of these free electrons around DESI galaxies. And so we've made measurements of this effect stacked around DESI galaxies. So we stack this kinetic Sunyaev-Zeldovich effect around luminous red galaxies in this figure, and that's what's being shown in the red points here. And this statistic is something called compensated aperture photometry statistic. And you can think of it basically as a cumulative gas profile around DESI galaxies. And the really interesting thing here is that these red points disagree at very high significance, both from what we expect from dark matter only, so that's shown in the orange line here, and also from hydrodynamical simulations of galaxy formation, such as TNG 300 with low-ish baryon feedback. But they do agree quite well with older simulations, such as the Illustris 1 simulation, which have significantly more baryon feedback. So these KSZ measurements are telling us that the gas profiles in the universe, at least around these LRGs, are significantly more extended than what we expect from kind of more state-of-the-art simulations shown in blue. They agree actually with these older simulations with more feedback better. So there may be more feedback in our universe than some of these newer simulations predict. And so this has important implications for the scales that we can analyze in our lensing data, because the models that we apply typically come just from dark matter predictions for the matter distribution. We neglect or try to marginalize over these baryonic effects. And so this is telling us that maybe we need to worry about this a little bit more. And in the future, we really want to fold this type of measurement into our cosmological inference using these weak lensing statistics to really fully account for this effect. And so in the last few minutes of this talk, I want to tell you about how we can combine weak lensing and DESI clustering to improve our cosmology constraints. And before I get to the DESI Y1 data, I want to tell you about a really powerful way that we can use the DESI Y1 data to calibrate a much wider area. So the DESI Legacy Imaging Survey footprint, which is about 20,000 square degrees. And we can select galaxies the same way as we do in DESI, so the bright galaxy sample and luminous red galaxy sample in particular, over this whole 20,000 square degree footprint, and calibrate their redshift distributions using the actual DESI spectroscopy, which we only have a few thousand square degrees of in the Y1 data set at least, and use that to really calibrate redshift distributions over a much wider area and use them to do cross correlations with lensing. So that's very powerful. Even where we don't have overlap with the actual DESI footprint. So I'm showing you one such redshift calibration here for the luminous red galaxy samples. This is a figure taken from Noah Saylor's paper from this last summer. And these different lines here are just different tomographic bins that we've split the luminous red galaxy sample up into. And we can essentially perfectly calibrate the redshift distributions in this whole area, colored area that I'm showing you here, just using the DESI Y1 data. And so you can compare the redshift distributions in different regions where the photometry differs, and you can see there's a kind of a negligible change in these redshift distributions. So this is incredibly powerful, and we can use it to do essentially the highest signal-to-noise lensing measurements that we'll ever be able to make with DESI data or this DESI legacy imaging survey data. And so those cross-correlation measurements with CMB lensing are shown here in the top, combining cross-correlating Planck PR3 and 4, as well as ACT DR6 with these DESI luminous red galaxies in those 4 different tomographic bins I was showing you. And then on the bottom, you can see the autocorrelation of those galaxy samples. So this is an incredibly high signal-to-noise measurement, and also, you can see our best fit model to this data in black is quite good. So this is a study that was first done by Martin White in 2021 and followed up with ACT data and improved DESI legacy imaging survey data by Noah Saylor last summer. And the upshot of this result of this paper is that the structure in the universe is growing about 1 to 2 sigma times slower than we would expect from the cosmic microwave background itself. So it's relatively consistent, maybe a statistical fluctuation, but still a bit lower. So the black points that you see here are fiducial measurements of sigma 8 as a function of redshift. The dashed line here is the prediction for this growth of structure, assuming the Planck measurements in a lambda CDM model. And so, like I said, you can see about a 1 to 2 sigma deficit in power. And the other really cool thing about this analysis was it was the first application of a hybrid effective field theory model. So this is a model for galaxy bias that combines perturbative methods in simulations in a way that we think is very robust. So this is coming from the Emulous New Simulations in a paper. The model is coming from a paper that I wrote about 2 years ago. And we can do an analogous study by cross-correlating galaxy lensing with now the bright galaxy sample and luminous red galaxy sample whose redshift distributions are calibrated in the same way. This time doing this cross-correlation measurement over the full DES Y3 footprint, which is about 4,200 square degrees. So the DESI overlap with DES will only ever be about 1,500 square degrees. But using this technique, we can actually have access to the full DES footprint and make some very high signal-to-noise galaxy-galaxy lensing measurements, which you're seeing in the top for the 2 highest redshift DES source galaxy bins. And then the bottom, you're seeing the autocorrelations of the galaxy samples again. And the upshot of this work is that, again, we find the growth of structure or the S8 or the amplitude of the matter power spectrum to be consistent with the CMB measurements. So this is different from a lot of previous galaxy lensing studies, which you can see over here. And we think that this is due to a combination of the improved galaxy bias modeling that I mentioned before, as well as a more conservative treatment of galaxy intrinsic alignment. So you'll notice that these error bars are significantly larger than the error bars that you're seeing in these galaxy lensing studies previous. And this is because, not because the signal to noise is less, but because we're making significantly more conservative assumptions about intrinsic alignments. So like I said before, this is a very important systematic, and that's illustrated in this work as well. The black contours that you're seeing here are the fiducial modeling assumptions that we make for intrinsic alignments in this paper that are basically agnostic to the redshift and scale dependence of the intrinsic alignment signal as much as one can be. And the green contours that you see here, which are about 50% more constraining, are modeling assumptions that are much more similar to the previous galaxy lensing studies that had been done. So in order to make the assumptions that we used in this green contour, we really need to keep going and doing these direct measurements I was telling you about before in order to convince ourselves that that sort of modeling assumption is valid. And in the last few minutes of this talk, I'll tell you about combining DESI Y1 spectroscopy with weak lensing. Starting with galaxy lensing, so we have about 1,500 square degrees of overlap between our galaxy lensing surveys that I was showing you before and the DESI Y1 footprint. So black, again, is the DESI Y1 footprint, and the different colors here are just the different galaxy lensing surveys. You can see the areas of overlap here. And we've consistently measured the galaxy-galaxy lensing signals using these 3 different, in this case, 4 different galaxy lensing surveys, so SDSS, in addition to those 3 that I've been talking about for the rest of this talk, using the same measurement pipeline. And by doing this, we're able to really convince ourselves that the amplitudes of lensing from these different surveys are consistent with each other, modulo known issues with Y3 photo-Zs in HSC, and some additional variants on small scales in BGS. So the different columns here are different redshift bins of the DESI samples, and the different rows here are different lensing surveys. And so you can see they're all consistent with this dashed black line, which is a model prediction for what this signal should be based on the DESI clustering. And so this is a very high signal to noise measurement, and we're in the process of analyzing it. So we put out a paper validating the modeling for one type of analysis that we want to do with this data, which is a cross correlation between galaxy shear and projected galaxy clustering. So this is an improvement over what we can do with just the galaxy lensing surveys themselves, which use angular clustering. This projected clustering measurement still takes advantage of the fact that we have spectra for these galaxies to make higher signal to noise clustering measurements, and then combine them with shear and position shear correlation functions. So this figure here is showing you forecasts for the constraining power for that set of analyses. So the blue contours here are kind of what we expect from our fiducial analysis, and the red contours here are what we get when we analyze a suite of simulations, the buzzard simulations, using our fiducial modeling choices. And to the extent that the red contours overlap with the blue contours here and agree with these hash marks here, it tells us that we're confident in our modeling. Yeah, these are small shifts consistent with kind of statistical noise in the simulations. And we also want to combine these shape correlation functions with 3D clustering, and that's also work in progress that you should look out for in the next few weeks to months. And finally, I want to tell you about doing these Y1 cross correlations with cosmic microwave background lensing. So in this figure in red, you can see the overlap between the DESI Y1 sample and the ACT DR6 lensing map. So we can fold this cross correlation in to both the DESI galaxy clustering, 3D galaxy clustering measurements that were used to do the S8 constraints I showed at the very beginning of the talk, as well as the photometric cross correlations I was showing you previously. And when we do this, we get really impressive improvements. So what I'm showing you here on the left is a comparison between what we get from just the DESI 3D clustering measurements of how redshift space multipoles shown in blue, looking at S8 in particular here. When we fold in just the cross correlation with CMB lensing over the Y1 footprint, we get the orange contour. The green contour here is essentially the same result as I was showing you from the Saylor and White et al. Papers before. And the red contour is then what happens when we combine all of this. So we get a very, very significant improvement in constraining power when combining all this data. And in fact, we still get an improvement of about a factor of 2 over what we get from just the DESI data, even folding in BAO, reconstructed BAO data. So you can see this orange contour here is all of the DESI tracers combined with just the cross correlations for the LRGs. And so you can see this is about a factor of 2 improvement in S8 constraint. So that is really, really powerful and something that's very exciting. So with that, I'll conclude and just leave you with some takeaways. So by using DESI data, a number of important systematics and weak lensing analyses can be mitigated. And by combining weak lensing with DESI galaxy clustering, we can get a powerful avenue for measuring the growth of structure. We can get about a factor of 2 improvement in constraining power on S8, like I was just showing you. And you should keep an eye out for a number of papers described in this talk in the coming weeks. And also, I want to highlight that in Y3, we're combining lensing and clustering to both tease apart these systematics and improve our constraining power on the growth of structure as a key project. So we'll be under the same scrutiny as, for instance, the type of analyses that you're showing that Enrique is going to talk about in the BAO talk. So with that, I'll say thanks and leave you.